recording. How are you today? Great, wrong screen. Swap, thank you. There we go. So, we have three more of these, including this one. Um, I will once again remind everyone that the mask mandate is back in effect. If you are curious why, please raise your hand if you yourself or a member of your robot group has been sick in the past 2 weeks. Yeah, yeah. It's like your whole class. It's awful. The other stream is even worse. It is just sweeping like a couple of things, and especially COVID, are just sweeping through class. Um, and I will be a stickler for the masks because they do help. They're not perfect, but they bloody help. Yes, you can still have a drink in here, even though you're not supposed to anyway. But if you do have a drink, please have a drink and then put your mask back on your face. Cool. Let's get going. This week, um, we'll have an introduction. Um, like last week, it's going to be very much like last week. We're going to talk about a design philosophy, a tool of the week, and then we're just going to spend the rest of the time on SolidWorks. Next week, we're going to get into some heavier non how to use this program theories. But this week is really, I want to get you even more comfortable with SolidWorks. So show you some more of these sort of critical fundamental features. And then have some assignments because everybody loves assignments. And there should be time at the end for some work. So you can work that out. So, our design philosophy this week is human factors design, which is one of those things that seems incredibly obvious when you say it out loud, is that when we are doing design, we have to consider the people that will be using whatever we create. Um, so that sounds obvious, but that doesn't make it easy. So there's a pretty broad and well-known problem in design. All right, I need to stay in front of the microphone. People have been complaining that I do this and my comes back when they're listening to, and then it comes back when I come back to the middle, and the recordings aren't that useful when I do that. Um, so the problem is that when we're designing, we tend to design for ourselves. If it would work good for me, it would work good for you. The problem is that people are very different. People have different abilities, interests, sizes, shapes. Um, they'll interpret things in weird ways, and engineers are weird people. So we look around this classroom, and there's sort of the impression that we're a pretty diverse group. If we just sort of like look at our faces and our haircuts, we're like, oh yeah, we're all pretty diverse. But that is a hideous lie. This room is full of the sort of people that would attempt to apply for and successfully get into mechatronics engineering at University of Waterloo. You have a lot in common. You're a very tiny and specific and weird swath of the populace. So even if you make a design and everybody in this room goes, crushed it, it's exactly what I want, you leave this space and they may not be as universal as it appears. And we often engineer, we work as engineers in kind of those kinds of bubbles sometimes. We're surrounded by other people in our company, in our profession. And so we need to keep this in mind. So human factors design is a collection of tools and philosophies and ideas that focus on human interaction. How does a human interact with a thing? That involves physiology, that is, bodies. How does my body physically interact with the thing? How do I poke the button? How do I hug the teddy bear? Psychology, how do people think? Is like what you have created intuitive? Are they going to understand it? The culture that people are using it in. And this one, it gets quite hard because cultural interpretations of certain things can be quite different. Go around the world, streetlights are all sort of similar, but they're not all the same. Um, and just something as simple as that, like do I go or stop at this moment, can be quite confusing just based on those cultural differences. And the environment. And in this case, we're not talking about like global warming kind of the environment, but the space we're working in. For example, if I were to use uh, this mouse, we'll use this mouse as an example. If I were to use this mouse in this space, it's probably quite well designed. But if I needed to do the same thing, something that does the same job in a at like -30 when I'm wearing mittens, is it still a good design? So we need to consider where things are being used, what environment they're being used in. Is it hot? Is it cold? Is it wet? Is it dry? Are we standing up? Are we sitting down? So those are some considerations for human factors design. There are some branches of human factors design. You've probably come across these terms before. Ergonomics is about the physical interaction of a body with an object. We usually talk about it like, is it causing us like, the ergonomic chairs? Is it comfortable? Is it going to hurt my spine? Or ergonomic mouse, am I going to get carpal tunnel syndrome? But ergonomics is broader than that. It isn't just trying to prevent injury when you sit at a desk. It's all of that. How does my physical body interact? How do the motions of my limbs work in concert with an object or a space? User interface is interested in how I interpret the controls of the object. So if the object is more than something that I just pick up and put down, but something I push buttons on, twist knobs, need to adjust and control, how do I do that? How do I interpret that control system in a way that makes sense? And user experience is the really big picture. What is my whole experience of of an object or of a system? And usually user experience is more about a system. And oh no, it's not dead. I just faced away for a second. Um, so if we think about so user experience, we often have it in software. But if we think about a building, we can have a user experience of a building. Uh, Ergonomics, we're thinking about like when I open and close the door, is it too heavy? Is it too light? Is it easy to grip the handle? User interface is when I come up to the door, do I know whether I'm supposed to push or pull? User experience is from the moment I step up to the door to the moment I leave the building, what experiences do I have? Do the hallways make sense? Is the lighting comfortable? That whole bigger picture experience. I will tell you, in your careers, you will likely find these terms defined differently in different areas and used to mean very different things. For today, this is what they mean. Um, they're sort of catchy business words, so they get misused. I think I'm not misusing them. All right. Sometimes it's fun to think about these things in terms of bad examples. Good examples are sometimes hard to find. You're like, well, I didn't notice, which is one of the things that, is often ideal in user experience and ergonomics. It's like, I didn't even really notice that I was using it. I didn't have to think about it. Great design. How about some bad design? In this room, we have a wonderful bad design. We have light switches. You might be able to see them at the front of the room, especially if so you can see the glowing lights and the light switches sort of by the door over there and by the door over there. Got one here too. There are red and green lights on it. Guess which one means the light is on? It's right? Doesn't that make sense? Red means on, green means off. Why? Does that make that it's incredibly unintuitive? Why? Green is good, red is bad. Green is go, red is stop in our cultural context. And so whoever wired this up somehow wired those backwards or designed this whole system backwards in a very confusing way. Yeah. It is certainly not universal and biological, but it is pretty broadly true. But there are absolutely places where like green and red don't hold, like they aren't considered like go and stop. There's places where you have like, because red and green are basically from streetlights. There's places where it's blue and red. Red is broadly stop because it's bright. But I think there's places where the yellow is stop. Yeah. It is only a good design if the people using it understand it. So you could talk about the logic of this, but I will tell you the vast majority of professors who come in and look at this display and push a button and it does the opposite of what they think it's going to do is the vast majority. It's not just me. Um, and in that, like, I bet engineers, like whoever designed this, sat down and had an argument about which it should be, um, and they missed. Here's another example. This is an example of somebody trying to get something right and missing the mark. So this is a staircase with an accessibility ramp. So, you know, if you got a mobility device, if you got pushing a stroller or you've got a walker or a wheelchair, you can go up this ramp, and if you're just using the stairs, you can go up the stairs. However, if you try to go straight up these stairs, every fifth step, you end up on an angle. And if you're a little shaky or you're not paying attention, you're going to roll your ankle because suddenly you're walking across a ramp on an angle. Also, if you're using a mobility device, a lot of people who use mobility devices don't have great like fine motor control. That's why they're using mobility devices. And so if you're a little shaky and not really good with like tight controls and you get to the top of this staircase, you're just going to go over the edge as you try to turn around. It's a terrible design, even though they were trying really hard to fit a mobility ramp into this narrow area. So I like this one because this seems on the surface like we're trying hard. We're trying to get this right, and we just didn't think enough about how users actually use this, how I'm actually going to interact with this staircase. And now I get rolled ankles and people in wheelchairs going head over heels down a flight of stairs. I also want to bring to our attention a specific example. I'll sort of narrow this down. We're talking about really broad things. Anthropomorphic charts are a useful tool. These were pioneered by an engineer called Henry Dreyfuss. He's pretty famous in the world of design. Um, and they show things like proportions of range of motion, like what can a human reach? Where do our arms go? So I don't like, so if we're like, trying to design a workspace, we don't put something that's like 8 feet up over here. We can get a sense of how big people are, where we see, how we see. Here is another example. We've got a lot of our charts look like this, where we have our median person, like our totally average. This is, our very, it was in 1967, but this is our average adult male U.S. citizen. This is our 50th percentile. So half people are bigger than this, half people are smaller. Few people are right on it. And then here's our 97th percentile, and here's our second percentile. So 2.5% of people are this small or smaller, 2.5% of people are this big or bigger, and 95% of people fit in this range. Can anybody see a possible problem with using this chart to base our designs off of? Yeah? Yeah. 1 in 20 people won't fit. Because 95% sounds like a lot, but that's 19 out of 20. That means that in a room of 100 of you, 5 of you won't meet whatever this is designed for. Now, for something like, capitalist gain, where all you're considered about is like, what's going to sell the most like physical products, 19 out of 20, if you can get 19 out of 20 people to buy your product, you're doing pretty well. But when we're actually thinking about designing for humans, this can be a bit misleading. It also kind of encourages us to design for the mean. Let's tell a story. Once upon a time, back in the distant, distant past of 1950, um, the United States Air Force had a problem. Their pilots didn't like their airplanes. They're like, these cockpits are lousy. I don't fit. My knees are hitting my jaw. I can't reach the controls. And um, the Air Force went, okay, we want to make this better. Like, we need to make these cockpits better. It is important that we have excellent airplanes for our excellent pilots. And they measured their pilots, over 4,000 of them. And note that, especially at this time, but even true today, the Army or the military gets to pick their people. And they get to pick them based on whatever they want, including size and shape. So their pilots were pretty standard. They had to be tall, like there was a much narrower range than this. They weren't taking 19 out of 20 people. They were taking like 1 in 20 people. They had to be like, between 5'5" and 5'9" or something like that. Like it was a narrow range of people that they would take. And then they measured them, taking dimensions like this. Hip width, shoulder width, length of fingers, length of like hip to knee to ankle, ankle to toe. To figure out how big all their controls should be. How big should we make this cockpit? And then they measured all of them and they got their average and went, great. We've got our average pilot. We're going to make our cockpit to meet this average pilot. But thankfully, before they started manufacturing, one of the people working on the project looked at the numbers and went, yeah, we've calculated our average pilot. None of the 4,000 people we measured matches. Not one. So like you might be like, all right, that one has the average leg length, but their hand size is too big. That one has the average height, but their torso is unusually long and their legs are short. Or their arms are longer. And when we took that mean, we washed away all that specific personal information. And what they realized, and this isn't really shocking or weird to any of us now, is that one size can't fit all. And so they made their cockpits adjustable, which nobody's surprised by that. It's like, wait, you can adjust the distance from the seat to the steering wheel? That's in every single one of our cars. That was an innovation. The recognition that we have to make it adjustable if we're going to make it safe and functional and adapt to our pilots, because we can't make our pilots adapt to our cockpits. Same thing, flight suits, helmets, they just started producing more than one size. So that is our story about human factors design. Really, it's just a reminder that humans exist, and they are complicated, and they don't all look, think, act, feel like you, and in ways that you may not realize. And so if you are going to be designing for people, not everything we design is for people to interact with. Sometimes they're gears that go inside machines. But if you're going to be designing for things that interact with people, you have to think a lot about people. All right, let's move on to MTE 121. Welcome to MTE 121. I wanted to make a bit of a connection between your programming course and the programs we use. Because you are all programmers, we're about to start learning classes and object-oriented programming in 121. You have been interacting with objects pretty directly and object-oriented programming very directly all term. AutoCAD is very object-oriented. You'll notice all term I've been calling lines objects, circles objects. Put a circle object down. Combine several line and circle objects into a polyline object. I guess it's lines and arcs. Every object that we create is a member of a class. When we create a line, that is one line object that is a member of the class that is called line. All lines are members of this class. That class defines all of the things that we can do with lines, how to make them, how to move them, how to delete them, how to measure them. So that's all what's contained in the class. And then whenever we create a line, we look at the class for instruction and it goes, oh yeah, here. This is how you create a line. This is how you measure it. This is all of the data that is associated with your individual line. If I want to copy it, part of the class is a function that includes instructions on how to copy lines. If I want to modify one of the points, it has instructions in the class as to how to modify the points of a line object. Circles, another class. The interesting difference between lines and circle class is that the circle has multiple constructors. So whenever we create a circle in AutoCAD, it's really just defined by its center and its radius. Every circle, when you go, like, that's all we need to know about a circle to place it on a drawing. But AutoCAD has multiple ways to create a circle. So you go, here, I want to give you 3 points of information. And AutoCAD will go, cool, give me those 3 points and I will make a circle object out of that, and I will figure out where its center and its radius is, even though you gave me different information. I wanted to sort of bring this to your attention, because for a few of you, you are long-standing programmers, and suddenly you go, I see the relationship between object-oriented programming and AutoCAD. For some of you, you like AutoCAD much more than programming. And hopefully, this will make a little bit of a connection between the two. And when Nasser starts talking about classes, you can go, oh wait, I understand AutoCAD. Maybe that will help me understand classes. Because it turns a few people's brains insides in. I also want to bring it up because we can use our powerful programming skills in SolidWorks. SolidWorks recognize the fact that it is a computer program, and you can treat dimensions like variables. We can create variables, we can create equations, we can base a dimension off of other dimensions and math. And that's one of the things we're going to do today. So, be excited. Let's move on. I'm jumping around a lot today. I know, I don't have a good narrative flow. I told you how to make a good presentation on Tuesday, and now I'm making a very mediocre presentation. There should be a flow, a narrative arc. We just have a bunch of different subjects to talk about. So, here's my segue, tool of the week. This week, we're talking about the lathe. Most of you have used a lathe now. It is for what we call turning operations. It's still a cutting tool. It's still cutting material off of stock. But we're doing it by turning the material and pushing the cutter against it, unlike a milling machine where we spin the cutter and move the material against the cutter. It's sort of doing the whole thing backwards. And what it's good for is making round things. Because the part is spinning, we are going to get rotationally symmetric cuts. There are lots of exciting ways to use a lathe. You can cut threads. You can chuck things in different ways and cut tapers and angles. But fundamentally, it's about making things round at specific diameters. Let's grab a very quick YouTube video of somebody cutting some brass with a lathe. So, you guys have played with the lathe, but you might not have been able to see that up close. So we have a cutter. This is from the back. We've got a cutter moving against stock, and as it moves along and presses into the material, it's doing a roughing pass and a finishing pass. Roughing pass, they took off like 1/16 of an inch. Now they're taking off a couple thou. and they're just moving that cutter in and out using the dials on the lathe. I would like to contrast that with the wood lathe. Metal lathe is a high precision tool. You've got typically close to a thousandth of an inch resolution, and it's very, very stable, so you can actually get that kind of precision out of it. That's why they're so big and heavy and made of steel. It's so they don't bend and jiggle and warp as you're trying to do your work. Wood lathe, same fundamental process. We have a spinning thing, and then we press a tool against it. But that tool is usually a handheld chisel. So let's grab a quick. And so you are pressing that chisel up against your workpiece to carve things out. Much more artistic. These are much faster tools to work with, but much less precise. Way less repeatable. You tend to be going by eye. Your tolerances tend to be much looser. The metal lathe, the focus of what we care about here, has many parts with specific names. I don't want you to memorize them, but I do want you to be aware that they have very specific names. So if you are going to start interacting with lathes, talking to people who are using them, you may need to learn the vocabulary. So you understand what the headstock and the tool stock and the carriage are. Some of the names are obvious. Bed is the long flat thing that like lays sideways. Um, However, like the tailstock may not be as obvious. It's the bit that slides back and forth, and you press it up against the bottom of your work, typically. Or you insert. Actually, no. Did you use a tailstock at all? I don't think so. No, because yeah, either you use it for like drilling out the center, or like pressing it up against your part to keep a long bar from wobbling. But we're using like an inch long piece, so it wasn't particularly necessary. Not all lathes have all of the same parts, but most of them have most of them. And the question that I ask every week after Tool of the Week, besides tools just being fascinating and fun, why are we talking about this? Because SolidWorks simulates lathes in an exciting way. Revolves in SolidWorks. That is what we're going to be focusing on this week. And that's what we're going to do before the break. And then we'll just play with revolves for a bit. And then we will start working on a specific part. So now I'm going to remember that I forgot to load SolidWorks. So you get to watch this exciting adventure of my not too shabby, but not incredible computer loading SolidWorks. Any questions? Well, this 45 seconds passes. Yeah. So yeah, if you like, absolutely, the shavings that come off of machining will get sold as scrap. They're not very valuable scrap most of the time because they're so thin that you get a lot of oxide. So when you melt them down, you get a lot of slag. But it's still absolute, like companies that do a lot of this will make hundreds of pounds of shavings a week. That's worth selling back to a scrap. Very rarely will machinists melt them down themselves, because very rarely do you have your foundry, the place that melts metal and makes ingots and casts it into things, be in the same place as your machinists. Those tend to be different buildings. Companies. All right. Revolves in SolidWorks. So last week we made extrusion. We made a sketch, and we then extruded that sketch along a straight path. A revolve does the same thing, but instead of the path being straight from our sketch, it is, it's circular. It has a constant radius. So we're just going to draw a sketch, pick a line about which, a straight line about which to spin that profile, and extrude it in a circle. So I'm going to do this a couple times, just making some random shapes, and then I will leave you to play, and then we'll come back after a break. So, just like last time, first shape we're making, I'm going to put it on the front plane. Doesn't matter which one. And I'm just going to draw like a random shape. It does not matter. Thank you. No, no, thank you. There we go. My mouse is being slightly uncooperative. I think I need to charge it. All right. So I'm just going to make do. There we go. Unenclosed shape. Of course, it needs to be enclosed because it was an open mat. If it was an open face, we would not have a solid with which to model. And then I want a center line around which to rotate this. I am going to, in my little drop-down menu, create a center line. I'm going to create a center line just vertically right there. And so this shape is going to rotate around the center line. Fantastic. Done my sketch. And there's my little preview of what this will look like. It is automatically picked it, like I only had one contour, so it picked that contour for me. And I put in a center line. So SolidWorks went, oh, you have a center line? I'm gonna guess that's the line you want to rotate things around. So let me create that, and then we can see, hey look, it's a circle with the center line as its center. Let me go and edit that feature, and let's play with what that can look like. So by default, it picks that center line as its center, but any straight line in this sketch, on the like on a more complicated part, any of those things could be my center line. So I'm gonna change that, and I'm gonna say, hey, this part of my sketch over here, let's make that my center line. And it makes a different shape because it's revolving around the center of that sketch I made. Let's go in again. I'm going to change that back to this being my center. And now I'm going to go and edit my sketch. You see I've got a bit of a preview here. I'm going to take the center line. And as I move the center line back and forth, you can see the radius of my shape is going to change. Once I cross over, it's going to fail because then I have like the same volume sort of existing twice inside itself. I could also, I'm going to take off my vertical relation here. I'm going to play with the tips. Oh, it doesn't like that. So as I change the angle, it changes the angle at which it rotates, and because of that, the shape that comes out. I'm going to get rid of this one. Get rid of this whole sketch. And I'm going to make, very quickly, I'm going to extrude a cube. From there, let's go. Smart dimension, bam. Let's make you 10 by 10, just so I actually know how big it is. And then blind 10. Hey, there's a cube. Wonderful. Hit check mark. Why did I make a cube? Because I want to rotate things off it. So I am now going to revolve a boss off of this cube. So I'm going to use the top of my cube as the sketch plane, and I am going to make, again, just sketching some shapes. I am going to make a semicircle. Trim this. Oh, nope, nope. I did not get my snaps right. Coincident. Yes, I would like you to be coincident. Lovely. Trim. Okay, so I've got a semicircle there. I'm going to hit OK. I'm going to hit OK. There's my sketch, just a semicircle. And now my axis of rotation, I'm going to rotate this about part of an existing shape. And so I can use existing features as my axes of rotation. Now I'm going to do the same thing, but rather than having using an extruded boss, I'm going to make, or sorry, a revolved boss, I'm going to make a revolved cut. So I'm going to cut into my front face here, and I'm going to do pretty much the same thing. Circle, and I'm going to go, yep, from you to center over to here. So there is my sketch. It's just a circle with a quarter cut out of it, 3/4 of a circle. And then let's pick our axis of revolution. If I pick this axis, that's the preview of the cut that it's going to make. Sure, that's great. Bam. Oh, look. It cut that curved channel through my part. Let's go edit that feature. Change my axis of revolution. And we'll get a channel up here. Just like before, we have all these options of what we can, like, we can go blind, we can switch direction. So I don't have to do my full 360 degrees. I could do like 300. And it won't go all the way through. Or I could flip my direction and go say, I don't want to go the full 90 through the part. I want to go 45. And then I'll only cut part way through my part. There you go. You can see it dead ends in the middle. If we change this into hidden line view, you can see, oh yeah, there it is, stopping partway through. So those are the two big construction features that we'll talk about today. And some other, I will definitely get into some other fun and exciting features after a 10-minute break. But I want you to play with revolves while we're taking a break if you're not doing anything else like, say, putting your mask back onto your face, because some people in this room seem to have missed that message, and going to the bathroom and getting a drink. So yeah, take 10 minutes, get SolidWorks loaded up if you don't already on a school computer or your own, and then we will do the work along found in the folder called sled support. Sled support. recently happened. It's probably easier to see on this screen, but so this little arrow up here, you hit collapse that, and they've just got the tabs. So if I click here, it shows up, and then on the bottom right, there's a pin. All right, folks, let's get back at it. I'm going to start a whole new part for myself and open the one that we're going to be making. SolidWorks, new part. And I have the folder open with all of the, again, sort of a step-by-step of the different things that we're going to create. So if you get left behind or if you accidentally delete or ruin something, you can just grab the next step in the process and keep following along. So what we are going to be making... Oh, actually, let's get that one. What we are going to be making as soon as it loads. I want it gold so I don't get confused as to which one it is. There we go. I've added some color to this one. We're going to be making this. So this is just a little round part with a couple flat faces. That should feel familiar. Things that you guys don't have, we have a little groove in here for a circlip or C-clip or spring clip. Different names for the same thing, which is a kind of fastener that you can put on round shafts. They're sort of semi-permanent because they're a pain to get on and off. That will clip around into this groove almost all the way around and prevent anything that's sort of stuck between here and that clip from sliding on and off. And they're nice because they distribute the load all the way around that groove, rather than like if we had a bolt, it would just be at the two ends of the bolt that it would be able to put that load on. Then we have over here a threaded hole. I will note that these threads are not real threads. Your SolidWorks, when we make a threaded hole, we're going to use the hole tool for it. It doesn't render the actual threads for it. That's a lot of processing power for something that's not necessary. Because when we punch a threaded hole in here, what we're basically telling SolidWorks is somebody someday is going to drill a hole and then tap that hole using a tap. And so it just sort of, sometimes it doesn't render it at all, depending on your computer and your settings. Sometimes it'll render little fakey threads to be like, this looks like a threaded hole, but it's not actually rendering those threads perfectly. I.e., we couldn't 3D print this. The threads aren't part of the model. They're just sort of recorded as existing. We'll get to that in a bit. All right. But we're also going to do something a little bit different for this model. Actually, let me open this one up. We are going to start to use the power of computers in the world of the future. And we are going to set up some global parameters, global variables in this case. SolidWorks, it's okay to use global variables, unlike C++. And with those, we can make adjustments. So under our equations folder here, if you open up the future one, we have a bunch of equations. And if I right-click on here and go to Manage Equations, you'll see I have all sorts of global variables established. And I can change a length and go, what do I want L1 to be? I want L1 to be 20 instead of whatever it was. I want D2 to be 120. And then when I hit OK, it's going to change shape based on those variables. So we're going to punch some variables into our model so that we can then update sizes and shapes later as things change. Oh, I forget the original sizes. Let me close this. Don't save, thank you. And reopen it and its original proportions. So the example that I'm going to be working to is this drawing. I would like you to take note, no thank you, that the dimensioning on this is terrible. we have formulas on our dimensions. That is very weird. This is made, this detail drawing is made just so we can make this part using SolidWorks off of it. Do not use this as good practice for dimensioning. Hang a lampshade on that and move on. And you can see most of our dimensions are based off of two variables. We have a base, which has a value of 100, and then this is 1.5 base. This is 0.75 base. Then we have full length, which is 200, and this is full length over 2. This is full length over 5. And so we are using these global variables to base a bunch of our sizes off of. So let's start with establishing how to make a global variable. So let me open up my new drawing. I have changed my settings so my equations folder always shows up here. I forgot how I even did that, so I couldn't remember how to undo it, and I'd have to go and Google to get rid of it. But for you, under Tools, so if you go up to the top here, under SolidWorks, let me pin this open actually, I prefer that pinned. Under Tools, there is this Equations. Hover there for a second, so SolidWorks menu, Tools, Equations. And with a drawing with no equations, this is how you get into here. And we're just going to add a global variable. I'm going to add the variable base. I'm going to put a little quotation marks. It's a string. And here I'm going to say, well, what do I want my base to be? In this case, my base is 100. Oh, I can even pick my units. 100 millimeters. That's my base dimension. I did, yes, I'm about to. I misbehaved. Bottom right corner. I should have changed my units to what I'm going to be working in first. It's always good practice. I sort of forgot. So, but I picked my units. I could have picked inches. And then even though I'm working in millimeters, it'll know the conversion between like 2 inches and millimeters. So I can, if I want, in my equations, which should now show up in your feature tree over here, or in your part tree. You should now have an equations folder. You can see the existing ones. And that little globe says, oh, I'm a global variable. If I right-click on there, I can manage my equations. I'm going to add, I could have added more than one. I just wanted you guys to see it show up in your feature tree. And I'm going to add in my second one, which is full length. And it has a value of 200, again, millimeters. Okay, so now those exist. They're just variables that, no matter where I go in this part, exist and I can reference. Give you a second to type those in. Maybe I'll pull that up again. Right-click on equations, manage equations. Base was 100, full length was 200. All right. Let's make a feature based off of these. So we're focusing on revolves, right? And I could make this part a couple of different ways. I could look at this as some cylinders stacked on top of each other, extrude a cylinder using extruded base, extrude another cylinder, but it's rotationally symmetric, so I am going to use revolve. And so, let's grab a pen. No. There we go. So, let's draw a little thing. So I am going to revolve a shape, but I'm going to revolve I'm only going to draw half, because when I draw half of it, and revolve it through a full 360 degrees, it will become the full diameter. So I'm going to draw the radius, revolve it, we'll get left with the diameter. Yeah, man. Oh, yes. Yeah. Yes, I will repeat, this is not a good drawing. Um, this is only here to give us dimensions. Some of the dimensions are missing. I didn't even dimension the chamfers. um, they're just really little. We'll add them in later. Um, so what I am going to draw is this shape. I'm going to skip a couple features intentionally. Should have zoomed in further before. So I could draw this groove in on my first pass, but I want to do that as a second one, just to show you how tools work. I am going to include this fillet. I'm not going to include the chamfers. So I'm really just drawing sort of the silhouette of half of this thing. And I'm going to rotate it along its central axis, and that will make the full part. All right, bam, bam. Go over here. Let's start. I'm going to make a revolved boss / base. I'm going to make it on the front plane. I am going to, it's useful to have a fixed point in your drawing, and I'm going to use the origin as my starting point. And I'm just going to really roughly sketch this out by hand. Do. Up, down, over. So this is very roughly the shape that I want to make. The first dimension I throw onto this, check myself out to make sure I'm not in a line command anymore. The very first dimension I throw on this should scale the whole thing. Sometimes you can mess that up if you throw in a dimension and delete it, or you've made a feature and then gotten rid of it and come back. It won't work, but it should scale the whole thing if this is your very first thing. Now let me show you, I don't think I talked about gestures last week, and I meant to. I'm going to do something magical. See how I'm currently in just my cursor tool? Now I am in my dimension tool. Now I'm in my line tool. Now I'm in my circle tool. Now I'm in my square tool. So what I am doing, let me escape out. If you hold down your right mouse button and give your mouse just a little bit of a wiggle, this wheel will pop up. You can customize this wheel. You can have more than 4 on it. I prefer 6. You can change which tools you have where, based on what you use most often. And depending what mode you're in, you can have different ones. So this is what my sketch wheel. If I'm in the feature menu, it'll be different. If I'm in your just the base part, it'll be different again. But what this is a gestures wheel. And if I drag upwards over this quadrant, it'll switch into that tool. So again, if I'm dragging downwards, now I'm in rectangle. Dragging sideways, now I'm in line. But you don't have to do it slowly, you can do it quickly. So this, you can get so quick with this, if you know where your gestures are, that you very rarely have to go up to this top menu. And you can just switch back and forth between things. So, that was a lot of me talking to just dimension this bottom line. And what would I like that bottom line to be? Well, according to my drawing, according to my drawing, which I will drag over in a moment, it is the full length, which is 200. So I could just type 200 into here. That would be fine. But what if I wanted to change that at a later date? Well, then I'd have to go back into the sketch. And if anything else was also related to that length, I'd have to go and modify them. And so we will use the power of computers. I'm going to double click on this dimension so I get up my menu. And I can, rather than typing in a number, I can type in equals. And then you'll see I've got, global variables is coming up. Functions, file properties. If I go to global variables, hey, there's my full length. If I put equals, if I just go to global variables, it'll copy the number. But if I put in equals, you'll get the little sigma before it. And that says, hey, this dimension is related to, has a formula that's related to some other dimension or value. Let me check my drawing for a second. And then, okay, that one's over 5, and this one's over 6. So this distance is full length by 5. This distance is full length by 6. I'm going to do that in 2 different ways. So this one's full length divided by 6, right? So go into my dimension mode. Up here equals global variables full length divided by 6. Math formulas just like you would in C++. Brilliant. This one, I'm going to do something similar, but rather than going into my global variables, I can pick other dimensions on my sketch. And so I'm going to say it's equal to this dimension right here. Oh, look, all of my dimensions have names. I can give them, I could customize this name. I'm going to call this one Steve. Is it a good name? No. But we'll remember it when we see it later. So that's going to be d equals d1 at sketch, which is this dimension, divided by 5. I wanted to show you that because we don't need to create global variables to still use these useful programming tools. I can say dimensions are equal to other dimensions. I can say dimensions are combinations. I can use any math. Let me do something very silly. This is not the actual dimension we want, but this length here, I could say that this one is equal to this dimension plus this dimension. So this dimension is now the sum of these two. And if these ever changed, this one would change too, because it's a consequence of those. Now that's not the right number, so I'm going to change this one, double click on the dimension. Oh, hey, there's Steve. What this is actually equal to is our base, but this is the radius, not the diameter, right? The base defines it's a base diameter. This is my base radius, so I need to divide that by 2. We're almost there. We have 2 blue lines left, which means our sketch is not fully defined. So this one right here, 2 ways we could do that. This is supposed to be 1.5 times our base. Like this one's diameter is 1.5 times our base. I could do this 2 different ways. I could say it's 1.5 times this one, or I could say it is equal to 1.5 times. Oh, it's easier to get our global variables first. Base times 1.5 divided by 2. I didn't really need the parentheses. So this is just like Excel, just like C++. You say equals, suddenly we're playing a formula and math game. And if we update one, any of them that are attached to each other will update. So we've got one more. I'm not going to throw a dimension on this one. I'm instead going to use a relation. This line, shift, click, this line, collinear. That means they follow along the same line. Even if there's breaks in it, they align. That is to say, they would have the same equation. If we made the equation of that line, they would have the same equation. They are collinear. everything we're doing in here is just SolidWorks doing the algebra geometry for us. You haven't hit rotation matrices yet, have you? Because, like, when you click on your middle mouse button and move it around, that's just a giant rotation matrix in 3D, very quickly iterating through itself. All right. I'm going to finish this part out and then give you time to catch up, because I know I've done a lot of steps in here. So I have my sketch. Everything's fully constrained. We have black lines everywhere. Wonderful. Oh, a thing I forgot to do yesterday and really should have. I apologize if anybody yesterday is listening to this again. I'm going to over-constrain something just to show you what that looks like. I've been doing this well. What if we do it badly? So currently I have this is 50 and these are collinear, right? So what would happen if I also dimensioned this and said it was 55? Oh, it's telling me right away. Hey, here we go. Adding this dimension will make the sketch over-defined. Do I want to make this dimension driven? That is to say, it's like an AutoCAD dimension. It's just reporting a value. Or do I want to leave the dimension driving? I'm going to make it driven. Oh, okay, cool. See how it's sort of grayed out? That's just telling me a number. Let's delete you. Let's over-constrain something else. Let's say, well, let's try to make this line collinear with this line. It's not going to work, right? It can't both be 75. Like, these can't be 50, 75, and these two lines line up. So I'm going to make them collinear. Oh no! Oh no, everything's terrible. And you see, they're showing up in red here, and a bunch of things are showing up in yellow. What that means is there's something like a red or yellow, like a red relation means I can't resolve this. Something is broken here. These two can't work together. Yellow means I still can't resolve this, but I can't figure out why. The reason I can't resolve these is because these can't be resolved. I need to do something about this bad relationship before it can start doing math. So yeah, basically yellow over-constrained, red impossibly constrained. So if I delete that collinear, it goes back to being happy. So if you ever see red or yellow showing up in your diagram, it means you're over-constrained or you're attempting to make impossible geometry, that it can't mathematically sort of both, like you're like, I would like you to be vertical and horizontal. It's like, I can't be both of those things. Please stop. Please remove one of these. I'm getting stressed. Okay. Bit of a tangent. I finished my sketch. Selected contours. Let's select my contour. That one, there's only one. Oh, I meant to put a fillet in. I'll go back and edit my sketch. My axis of revolution. I could get this to rotate along any of my external straight lines. I'm just going to pick some different ones to show you some different shapes. But I want it to rotate around the middle, because that bottom line was the center of my part, right? And there we go. There is my basic part. Now, I meant to, in that sketch, include a fillet. So I'm going to go back into my part. If I click on my part in the feature tree, I can edit my sketch. I'm going to go in, and I'm going to put a fillet in. Fillet, just like we had in AutoCAD. What do I want to fillet, and what parameter do I want? So the entity I want to fillet is this corner right here. Oh, look, there's a preview. And what parameters do I want? Well, I want this to be, according to my diagram here, my base diameter divided by 10. In most of these windows, you could hit equals and it will come up with the dialog, but not all of them. Hi, yes. What is the difference between sketch fillet and feature fillet? The difference is the fillet is in your sketch instead of it being its own feature. Sometimes you, when you're making your sketch, you want to put in the curves. Sometimes you want to add them later. That's it. It is about order of operations and preference. Okay, so I'm just going to put in like 7 here for a second. So this one won't let me, I could type in, if I knew exactly what I wanted to type in, I could type it in here. But this particular dialog doesn't like equations, but that doesn't mean I can't go in later and grab that dimension and put in an equation, because I can always go back and edit. Norp. Done. Done. There we go. Now I've got the fillet. All right. That was a lot. I know that was a lot. I hope most of you are keeping up, but we'll give you a few minutes with the TAs up and wandering around to help you out with these parts. let us very quickly play with our global variables. So if I go in here to my equations and manage my equations, and I decide, oh, I don't act, my full length isn't 200, it's 100. Let's just switch these. Let's make this one 100, and let's make this one 200. If I've done a good job setting this up, everything is going to adjust based on my global variables. So you can see some of the power of this. And we'll talk in future weeks how to do something called configurations, where if you want to have multiple versions of a single part, you can do that. Global variables aren't really for that, but it's useful to know about them. Global variables are very much like, they're basically in C++ equivalent what we use our global constants for. Being like, we're pretty sure of these numbers, but maybe someday they'll change, and we want them to be easy to find and easy to adjust. All right, next thing that I want to add is the flat faces. How did we do these flat faces on our keychain? Well, we took our milling machine and we just milled these flat. We removed material. The equivalent here, unextruded cut. And I could do this a few ways. I could do it from the top and then the bottom, but that would require two different features, right? And they're totally symmetric about the center here. So I am instead going to go from the end and carve back into the part. So I'm going to look at the end of this part, and I'm going to make an extruded cut that goes into it. And so, extruded cut right here. Select a face. I'm going to go to the end of my part. And I am going to do something I didn't do last time. I'm going to make an oversized cut. So last time we made cuts that lined up perfectly, right? We were exactly to the edges of our part, and they were snapped to the edges of our part. I'm going to make my cut purposely too big. I'm not going to worry about it having it like making exactly this little sort of crescent-shaped slice of my circle. I'm just going to make a rectangular cut and then decide how big that rectangle should be. And I don't just want it floating off in space, so I'm still going to snap it to my circle. So I'm going to select my circle and that and say I would like you to be tangent. And then I'm going to grab that edge in my circle and say, hey, you, I'd like you to be tangent. And this edge and my circle, and say you guys are you're going to be tangent. So I have this rectangle that is tangent to the edges of my circle. So if my circle grows, my rectangle will grow. If my circle shrinks, my rectangle will shrink. But it's definitely too big. Like I am cutting a swath of space that's just empty. When I extrude this back, we're going to get like only the parts of that rectangle that actually touch the body of this are going to cut away. And that's fine. Really, I am just doing this so that you can see that having a cut that's overextended is okay, as long as it doesn't interact with any geometry you don't want it to. The next thing I'm going to do is I'm going to recognize that the top and the bottom of this are symmetrical, right? So let me make a center line through the middle of my circle. So again, line, little drop-down menu, center line. Just turned it off on myself. And I'm going to snap to the quadrant snaps of my circle. Go straight across. There we go. Nice horizontal center line. Oh no, come on computer. Oh, it's having some feelings. Don't have feelings, thank you. We're being recorded. And what I'm going to use this center line for is to mirror this rectangle. Just like in AutoCAD, we have a mirror function. So I'm going to be like, hey, mirror, what entities do I want to mirror? I want to mirror this rectangle. What do I want to mirror this about? I would like to mirror this rectangle about this center line. Do I want a copy? Yes, I want a copy. I want to keep both. I don't just want to flip it over, I want to flip and copy. There we go. Now I've got two. Wonderful thing about this, with the power of computers, it keeps it mirrored. We have symmetrical constraints on. So you can see this little, like the little box with the line through it, that's a symmetric constraint. So it is keeping all of these features symmetric to each other. So you can see, highlight the various bits, like, oh, I am symmetric to each other about that middle line. I am symmetric to that one about that middle line. So I can drag this back and forth and it'll stay symmetric. Also, that means I could dimension the distance between them. See, everybody's playing with my window. Yeah, man? Thank you, man. Um, so I'm going to dimension the distance between those. And according to my dimension drawing, or my detail drawing, that is, oh, don't want that tool anymore. Thank you. Back to select. That distance is 0.75 from face to face. Oh, that's a badly laid dimension. Anyway, 0.75 times the base. Oh, it's such a terrible drawing. Oops. Equals global variables base times 0.75. Check. There's my drawing. Let me extrude that cut back. And I'm going to, so if I extrude it back to here, you can see it's going to cut away that rectangle. If I extruded it too far, it would cut a rectangle through there. We don't want that. But just like in my dimensions, if I hit equals here, I can put in a formula for my extrude distance. Global variables, and that is full length divided by 2. And there's my extruded surface. All right, give you a minute to catch up on that. Questions if you have them. Between there was basically
Trim it. Or you just multiply things by 2 because you're good at math.
All right. We've still got TAs running around if you need help with this, but I want to keep going. We've got a lot of steps left. That said, if the TAs are talking, they should do it quietly. There we go. So, next up, flat faces, tapped holes. Oh, next up, let's add that little groove. So in our drawing, we have that groove for the circlip, right? Just a little tiny one, 3 millimeters. Oh, I really need to fix this drawing. 5 millimeters in from the end. Um, and its depth is very skinny. Its base, oh yeah, it's the base -3. So let's put that groove in. Now, a problem we're going to have, and I should have done this, I meant to do this before we put the cut on, so I'm just going to hide this for a second. Oh no. Oh no. Oh no, 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 no. Unhide, show? That's very weird. All right, well, never mind, we'll leave that. But I want to draw over here, and I don't have a surface that I want to draw this on. Like, these faces aren't in the right place for me to draw my sketch. I wouldn't be able to revolve it the right way. I need the middle of this part. Now, those planes that I had to begin with, front, top, right, they're there. They still exist, but they're invisible. So when I try to make a new revolved, oh, I don't want a revolved base, I want a revolved cut. When I make a new revolved cut, I can't select them. But I can. I just have to make them show up. 2 ways to do that. You see I have this little collapsed part tree in the upper left of my drawing space. I can expand that out and pick anything from there. I also have my visibility over here. And the top right one is the primary plane, so I can bring them back if I want. So now I can pick my front plane, and now those are ugly and I don't want them here anymore, so I can hide them again. But there's my sketch plane. And all I'm doing is cutting out a little rectangular group. So I'm just drawing a little rectangle. It's going to be coincident with the top there. There's my rectangle, lovely. And we want that to run around this whole ring. I need an axis around which it can revolve. So I'm going to put down a center line. I have a nice easy thing to snap to here because I made my whole part on the origin. Like my part is centered on the origin. But if I didn't have that, I could still use other features of my part, because this edge over here, I could snap to its center. If I didn't have that, I could sketch things out, tracing my parts to create a center. So yeah, I'm just going to snap to the center of this, bring it over to the center of my origin there, and there's my center line. That's the line I'm going to revolve around. Now I need some sizes. There's one that's very easy. This one, this was just 3. I believe, and the distance from here to here, this one was just 5. But this one is going to require some math, because it is base diameter minus 3. But that's the diameter, not the radius. So let's grab base diameter out of here. Base diameter minus 3 divided by 2. We can do fancy math. I mean, this isn't fancy math. We've got sines and tans and etc. all in there. There we go. Base diameter divided by 2 minus, or base diameter minus 3, parenthesis, divided by 2. And that's my sketch, just a little rectangle. We have a center line, so we know we have something to rotate it around. To check. Automatically guessed that the center line, only the single center line that I drew, is what I want to rotate it around. SolidWorks is just going to guess that for you. It's guessing that I want to do it blind a full 360 degrees, which is in fact what I want. And there's my circlip groove. So I could have done this as my initial revolve. I could have drawn in that little cutout, no problem. The only reason I did it this way was to show you the revolved cut tool. Also, it makes it a little bit more adjustable if you're like, well, the purpose of this thing here is my circlip groove. So if I come back to this drawing later, I can go, if somebody comes back to this drawing later and goes, no, we've changed the circlip, they know, oh, all I need to do is edit this feature. So it's a little bit more helpful going forward. You can bust up your features into meaningful components. So somebody else coming back to this drawing, even yourself in 2 years, when you go, well, we've modified the part, but I don't remember what I did 2 years ago. Your names and your features can tell you a bit of a story. Sometimes it's about what is easiest. Sometimes what makes the most sense in the future. But that is our circlip groove. Just a little cutout. Give you a minute, and then we'll start playing with holes. Let's play with holes. So if we have a look at our drawing here, we have this hole right here in the top of our face, and it says it's a 1-12 UNF through hole centered on the flat face. I have exciting news. This callout, the through hole size, and the thread callout. So this is this is our pre-drill through hole, and this is the thread callout. I didn't type this. SolidWorks typed this for me using the hole wizard. It's a wizard. So we're going to punch a hole through this using the hole wizard. So when I click on the hole wizard, I get a very like a fairly in-depth menu down the side here. I have different kinds of holes. I have counterbores, countersinks, through holes, fancy weird counterbores, hexagonal holes. Like I've got slots. So I am going to pick a straight tap because we are making a straight tapped hole. And then I'm going to look at the standard. What standard am I going to? Oh, look at all of the different types of holes there are. These are all of the different types of taps, of threads that exist. Well, there's more than this. These are just the ones that SolidWorks has in its standard library. Fortunately, the one that we're using is up at the top. It is ANSI inch. It is a 1-12 UNF. That is an ANSI inch thread callout. It is a bottoming tapped hole. It is not a pipe tapped hole. It is a bottoming tapped hole. And what is our size? Oh, look at all of our sizes in here. There are many. Oh, wait, yeah. I misclicked. I accidentally clicked on straight tapped hole when I was trying to get back to bottoming. So here we have so many. First we have our numbered. Then we have our sizes. We're pretty close to the bottom. We're doing a 1-12. That's a 1 inch, 12 threads per inch UNF. So I think that should be UNC. Anyway, it's so 1-12 bottoming hole. We have more options on here. We can add countersinks. We can decide whether we do we just want the through hole? Do we want cosmetic thread? Do we want to have a render how do we want this to be show up on our drawings? We can adjust our precision down or our tolerances down at the bottom, but we're just really going to leave it with threaded hole 1-12, nothing else fancy. Through all. We're going all the way through the whole thing. And then up at the top you'll see we have a positions tab. Where do I want these holes to go? Fairly commonly, select a face or a sketch. So if I already have a sketch, I can pick that. But I'm going to pick this face because this is where I want my hole to be. And I could put multiple holes in if I want. I don't want multiple holes. I, in fact, wish to delete those holes that I just made, except for one. But this isn't properly located, right? This is I just sort of slammed that in. How do we locate it? Well, we need to use some other geometry to reference the location of the center of this hole. How have we done that in the past? With our sketch tools. So you'll notice in here, it's automatically thrown us into the sketch world. And I'm going to use a line, and I'm going to make a little cross mark, because this is supposed to be in the center of this face. So I'm going to cross two lines, and where those lines cross will be the center of the face. So from this corner down to that corner. Oh dear, I accidentally got out of my edit that feature. Go back into positions. Okay. So, accidentally clicked out of my feature, had to go back into it. So, line 1, line 2, bottom corner to top corner. check. Now these two lines, oh, stop that. No, yeah, no, I got it. Misclicks are great, especially when they're on video. Positions. All right, right click, back into select mode. There we go. Hey, this line, you should only be for construction. This line, you should only be for construction. And now I want to grab the center of this circle, shift both of my lines, and one of the relations that comes up that I'm allowed to use is intersection. So it's going to try to put that point at that intersection. Boom. And now I'm going to hit my check mark, and I will be happy with my hole. So the settings that I have on mine are pretty basic. It's not rendering the threads here, but you can see we've got an inner hole and like an inner ring and an outer ring. That's telling me this is a threaded hole. It's just letting me know, hey, this thing here, this is the inner is the through hole diameter, and then that outer ring is your major diameter of your threads. Let's do one more hole with our hole wizard, and I will leave you to play with the hole wizard. So we have a hole running through the whole length of this. It's just a 1-inch hole right in the middle. Hole wizard. We were on threaded hole. I just want a through hole. It is again, well, actually, let me describe my villainy here. This whole thing was dimensioned in millimeters. And we have a 25.4 millimeter hole. This is where you as young Canadian engineers have to start recognizing when the dimensions might be telling you more of a story than they seem. Because what is a 25.4 millimeter hole in reality? It's about this big. You're not wrong, but it wasn't the answer I was looking for. Yes, it's 1 inch. So sometimes you'll see really weird fractional, like millimeter or centimeter and millimeter dimensions, and you're like, oh, it's an inch, or it's 2 inches, or it's an eighth of an inch. And you'll just start to notice and recognize common inch dimensions in metric, and vice versa. So 25.4, that is a 1-inch hole. So through hole. Pick our standard, ANSI inch. If we looked under metric, we would not find a 25.4. That is not a standard metric size. Sizes, inch is at the very bottom, which gives you a sense of the range of utility of the hole wizard. In and around about an inch, that's about as big as like with drilled holes get. And that's usually what you're using the hole wizard for, is to make drilled and tapped holes. Anything bigger than that is more of a bore hole, and then usually you use your extruded cuts for that. Location, oops, positions, I want it on the end. And again, I made my whole part based around the origin, so I can just click on that. But if I didn't, I can hover over the edge here, and then I would get a center snap to work with. And look at them beautifully intersecting in the middle there. All right, give you a few minutes to play with your holes. with a couple of chamfers. So we like chamfers. We like to have them on our leading edges so they're easy to slide into locations so they don't slice our fingers open. And on this, we have chamfers on the ends, here and here, and on the inside, our leading edge of this hole. Now we might call this chamfer a countersink, but it's not even a full countersink. It's just taken off the edges. So we have some 2mm chamfers all over the place. Now I could do that with revolved cuts, but that sounds like a pain. So we're gonna use our fillet tool. Like underneath our fillet tool, there's a little drop down arrow, and there's chamfer. And like our fillet tool, I can pick multiple edges. I'm going to pick this edge, and it's not going to work because the default one here is too big. So it's like 10mm is going. I can't do that. I'm interacting with features in a weird way. In order for a chamfer to work, I need a contiguous edge. So I'm going to drop this down to 2mm. There we go. There's our chamfer preview. And I'm going to add a couple more in. I'm going to chamfer this edge. I'm going to chamfer this edge. I'm going to chamfer this edge. And you'll notice I can select things that aren't just edges. Edges are an easy way to do a chamfer, but if I select a whole surface, it's going to chamfer every edge that it comes up to if it can. Oh, look, it's chamfering top and bottom of that. I don't want that. I'm going to look at my list of chamfers here, pick the one I don't want, get rid of it. I'm going to go back into the chamfer tool for a second just to point at some things. So you'll notice how we define our chamfer. We have a bunch of different options. The ones we're used to in AutoCAD, angle and distance, or distance and distance. We can have some weird ones if we're not at exactly like coming at it at a nice angle. We can have assume even distances, but we want a specific length. We can have wacky corners not getting knocked off. If we just want to like knock a corner off at a vertex. And that's basically it. That's your chamfers. All right. That is the end of our SolidWorks for today. I'm going to talk a little bit about the assignments, and then the last 20 minutes, half an hour, you should have to work on SolidWorks assignment this week. I know you have a lot going on, and there's a lot of weird nuances to SolidWorks, so it's nice to be able to work on it in the lab. So I'm going to jump back to my, actually, the only thing that my slide says is assignments, so maybe I will instead open the assignment. And we'll talk a bit about week 8 assignments. We have 2. Let's start with the second one. Again, we are SolidWorksing a part from the Formula SAE car. This would go in and be part of that clevis mount that we created. Here is, again, kind of a weird detail drawing of it. You've got all of the details on here, but you'll notice a bunch of them don't have numbers. There is brace and there is shaft. That's because I would like you to use global variables for this. So establish a brace and a shaft. We have a little table here. There's 2 sizes. So start with one of them. You've got brace, shaft, and shaft length. Do your whole drawing. And then just like last week, take your screenshots with your 4 views, 3 orthographic, 1 pictorial, and then adjust your global variables and take those pictures again. Submit both. So we have 2 versions of the same thing, which if you have done your dimensions right, if you have used your variables appropriately, if your formulas are accurate, you're just going to type in those 3 different numbers and bam, it'll change sizes, shape, and proportion and look exactly correct. And if you haven't, you will be shocked and appalled. a little heads up, this little weird wobbly feature here on this part looks difficult and complicated, that you don't know how to model it. A hint, you don't have to. SolidWorks is going to do that work for you. Think about order of operations and the sort of things that we've done in this class. That is a side effect of other operations. You're not directly modeling this wobble thing. That is a side effect of interacting and intersecting geometry. Assignment 2, we've been doing freehand. The most common place for somebody to have to freehand and have someone else look at it is in a meeting on a whiteboard. And so, to practice your freehand skills and to expand them into different mediums, this week, our freehand assignment is to pick 2 Lego pieces, stick them together, and draw them in isometric view on a whiteboard or a chalkboard. Chalkboard's fine. It needs to be at least a meter big in both dimensions. We can tell because you have to take a selfie with it. I had a little doubt about this, and I was like, oh, do I really want people like submitting photos of themselves? Like, I see your faces every day. It's not a privacy issue. So yes, so you'll be submitting a photo of your drawing and of your planning drawings. I'd like you to plan it in your sketchbook ahead of time. So figure it out in your sketchbook, draw it on a whiteboard, submit a photo of it and a selfie with your beautiful drawing. I will say, you may find this difficult. Whiteboard markers and chalk behave very differently than pens and papers. Pens and papers. Pencils and paper. Wow. So you might find it a bit weird. You can use any classroom that doesn't have people in it. No, we are not providing whiteboard markers for you. There are many places you can buy a whiteboard marker. South Campus Hall, Michael's, most convenient stores. One warning I will give you is you may want to do this not the night before, at least not all of you, because you may notice there are 250 of you between the 2 streams. If you all decide to do this on the same night, it may be hard to find an empty whiteboard. But there are plenty around. Classrooms when they're empty. Weave Lab, most of you have them in some of the rooms in your residence, like some of the study halls. Questions or concerns about these assignments? All right, then we have a ton of time left. A good chunk of you can probably finish your SolidWorks assignment for the week. In the period we have left, we will be around to help and work with you. Question for the class or question for me? All right. Then I will stop this recording and we will move on to just hanging out time.